Um, so the unit vectors can be expressed by e to the I theta. That is what we have found. And moreover, there is one more thing. If I multiply this by e to the I theta by I, e to the I theta, as you know, is cosine theta plus I sine theta. If I multiply this by I multiply this like this. So it becomes, what does it become? It becomes I times I is minus 1, as you know. So it becomes minus sine theta plus I cosine theta, isn't it? So if this is theta, think about it. Now, it is this unit vector has a component of sine theta in the x minus sine theta in the x direction, and the cosine theta in the y direction. So actually, this is this unit vector. So this is I times e to the I theta. Okay. So basically, multiplying by I is equivalent to rotating a unit vector 90 degrees. Okay. Because as you see here, now this angle is theta. This angle has become theta. So that its y component is cosine and its x component is minus sine, as you see, because it's a minus now. If I multiply it again, I times I e to the I theta, okay, it makes I squared e to the I theta, but I squared is minus 1, minus 1, so it is minus e to the I theta. So e minus e to the I theta means it's in the negative direction. So it is this. This is I squared e to, well, let me write it right here. This is I squared e to the I theta. So I multiplied it by I again. I rotated my vector again a 90 degrees more, okay? And if I multiply it again, I cubed e to the I theta. I cubed is, as you remember, is minus I e to the I theta, isn't it? I cubed is I squared times I. So it is another 90 degrees of rotation. So this is I cubed e to the I theta. And if I have I to the 4 e to the I theta is simply e to the I theta. So this is again another rotation. So multiplying by I means 90-degree rotation of the unit vector counterclockwise. Okay? 90 degrees counterclockwise rotation is multiplication by I is equivalent to rotating our vector 90 degrees counterclockwise. This is an important result, and we will be using this over and over again. There are a few more results. Let's say that you have two vectors. Let's say R1 is R1 as a vector is R1 e to the I theta 1, and R2 vector is theta 2. So we have two vectors, like this is R1, this is R2 with theta 1 and theta 2, let's say. we can manipulate, add, or, addition is kind of easy. We just add vectors, but multiplication is kind of important. If you multiply these two vectors, R1, R2 vector is simply R1 times R2 times, but e to the I terms simply have to be added up. E to the I, theta 1 plus theta 2. Okay. And if you have R1 divided by R2, then you will have the magnitudes divided, e to the I. Well, it will be theta 1 minus theta 2. Okay. There is something called the conjugate of a vector. For example, if R1 is e to the, sorry, R1 is, oh, yeah. The conjugate of this vector, R1, let's say vector conjugate, is simply R1 e to the minus I theta, which means in the complex plane, if this is R1, R1 conjugate will be something like this, or R conjugate. So if this is angle theta, this will be angle minus theta. So the conjugate is the mirror image of that, sorry, vector, okay? Over the, taking the x-axis as the axis of symmetry. And you have R1 times R1 conjugate is going to be the magnitude R1 squared, because these two are going to cancel each other when they are added up. And one thing that you should also remember, that if you add up two unit vectors, e to the I theta, well, not two unit vectors, e to the minus I theta, and e to the I theta and e to the minus I theta. Okay, if you open them up, you will see that this will be equal to 2 cosine theta. This is an important result which we will be using later on. Okay, so it's a very brief review of complex numbers. And also remember that if you have, I will do that later on, but if you take the derivative, like r equals, let's say, I theta, the derivative of this dr dt is going to be r dot e to the I theta plus r I theta dot e to the I theta. So we will be using the chain rule, but we will use this later on when we come to velocity analysis. Okay? Just keep this in mind for the time being. I will review that anyway later on. Let's do something else. Now let's try to write our loop equations in terms of complex numbers, because in complex, let's say, representation. Again, our typical 4-bar. Let's call this point P. So what was our vector equation? A0A plus AB is equal to A0B0 plus B0B. Well, you can also write this as, for example, A0A plus AB plus BB0 equals A0B0. It can also be done that way. But now this makes things a little bit easier. This vector now, this A2 and theta 1, 2 vector can be represented by A0A can be written as A2 times e to the I theta 1, 2, as you can see. Okay. Therefore, and the same is true for A3, A4, etc. So that we can write the loop equation as follows in a more compact way. A2 e to the I theta 1, 2 plus A3 e to the I theta 1, 3 is equal to A1 plus A4 e to the theta 1, 4. Okay. As you know, we can write e to the I theta in general is cosine theta plus I sine theta can be divided into this. So for each of them, we can write sine theta and cosine theta. So we can write this as this equation as follows. A2, let's say, cosine theta 1, 2 plus I sine theta 2 plus A3 cosine theta 1, 3 plus I sine theta 2 plus, not plus, equals A1 plus A4 cosine theta 1, 4 plus I sine 4. Okay. Now, therefore, here actually again, it seems like we have one equation, but no, we have two equations because we have the real and imaginary parts that are independent. These they are independently correct. They have to satisfy them. So we have two equations: A2 cosine theta 1, 2. This is the real part. This is A3 cosine theta 1, 3 is equal to A1 plus A4 cosine theta 1, 4. And in the imaginary part, A2 sine theta 1, 2 plus A4 sine theta 1, 4. And these equations, remember that these are same as before. It was the same equation we had before. Nothing has changed. We just use the complex number representation. Uh, it is kind of simpler to express because this equation we have over here is simpler to express. But the solution will be the same because it expresses the same equation. And also, for this point P, we can write the following. A0 P is equal to A0A plus AP, which is A2 e to the I theta 1, 2 plus C, not A3, but C, e to the I, its angle, which is theta 1, 3 plus gamma. Let's go back. Here, the angle that C makes with the horizontal, as you see, is theta 1, 3, which is this angle, this very small angle, plus gamma. So this is theta 1, 3 plus gamma, okay, this angle. So it is, where is it? Theta 1, 3 plus gamma. And we can write this as, if you like, A0P is, let's say, x coordinate of P plus the y coordinate, but you can write it as Py, okay? So that we can, after solving it, this part is, after the equations are solved, this part is known. So its real and imaginary parts can be expressed as Px and Py. This is, let's say, known if theta 1, 3 is solved. So Px and Py can be expressed so that we can draw the path of, let's say, this point P. So the path of, it can be drawn, and that path of point P is called sometimes the coupler curve. So we have analyzed, therefore, the, well, we didn't solve it yet. We have just written the equations for the four-bar mechanism. And let's do the same thing for slider crank mechanism. Okay. Now I will draw a crank. Not a very good drawing. This is the crank, let's say. This is the connecting rod, and this is the slider. Okay. Now the angles well, let's call these, this is A2, this is A3, AB is A3. Now, this slider crank is an eccentric slider crank, so this distance is a fixed distance, which I will call C, and that is the eccentricity. Okay. So A2, A3, and C are fixed link lengths. Okay, angles now. This angle is theta 1, 2. The crank angle is theta 1, 2. Now this link 3 might have an angle of, we measure them counterclockwise, so it's a big angle, it looks like. If you measure it from here, this is theta 1, 3. Okay. Theta 1, 3 is an unknown. There is one more unknown here, which is the distance between, the horizontal distance between A0 and B, and that we will call, I didn't number the links. This is 2, this is 3, and this is 4. This distance is called S14. The distance of link 4, well, from the ground, if you like, okay? With respect to the ground, rather, a fixed point. So this is S14 would be the variable. So the fixed things are, if I write it here, A2, A3, C are fixed, and variables are theta 1, 2, theta 1, 3, and S14. And usually this is the input. This will be the input. Actually, it might be that the S14 might be the input as well in some cases. It is possible. And we might want to find S1, theta 1, 3, and theta 1, 4. In any case, we want to write the loop equations here. Can I write it here? I don't know if I can. It would be much better if I write it here. Okay, let's write it here. The loop equation is as follows. Let me draw the vectors first. A0A plus, let's say AB is equal to A0B. A0B is this vector, but it can be resolved into its horizontal and vertical components also. So I can resolve it into, let me use this one, plus this one. So let me write A0A plus AB is equal to A0B. Which I can write as A2 e to the I theta 1, 2 plus, this vector, plus A3 to the I theta 1, 3 is equal to, well, it's the horizontal component S14 plus I times C. I times C is the vertical component. So this is basically our loop closure equation. Okay, so this is our loop closure. We can now write it as divided into real and imaginary parts. Let me skip the details and write the real and imaginary parts. Real part is A2 cosine theta 2 plus A3 equals, the real part is S14, and the imaginary part is 2 plus A3 sine theta 14, sorry, 13. Let's see. Well, actually, this is an easier equation. You can simply solve for theta 13 from here, because theta 12 is given, c is a constant. Theta 13 can be solved, simply from this. It's a nonlinear thing, but it can be solved. And if you can solve for theta 13, substitute it into here and solve for S14. It's easier to solve here. So the given theta 12 you can easily solve for theta 13 and S14 from here, which gives you the solution for the solution for our equation. Okay. Now, actually, there is another possibility for the loop closure equation for the slider crank. Let me write it here. Just to show you the flexibility here. Let me draw the slider crank again. Let's say that we have the slider connecting rod. Sorry, the slider is this one. This is C. Now, we can, for example, use the following loop closure equation. Instead of writing, let me just, this is A0, A and B. Instead of writing A0A and AB is equal to A0B, I can write, for example, A0A is equal to, let me just draw it here, A0B plus BA. This is also possible. So A0A is equal to A0B plus BA. Now BA is a vector that starts from B and ends at A. So we have to define an angle for that, and that will be this angle. It's not theta 1, 3, but let's call it theta 1, 3 prime, okay? And theta 1, 3 prime actually is simply this theta 1, 3, which we have defined here. As you might remember, this was theta 1, 3, minus the angle pi, 180 degrees less, okay? So I can write the following. A2 e to the I theta 1, 2 equals A0b is S14 plus IC plus, yes, A3 e to the I theta 1, 3 prime, because BA is A3 theta I e to the I theta 1, 3 prime, as you see here. So, as you see, AB is a vector, which is A3 e to the I theta 1, 3, and BA is a vector, A3 e to the I theta 1, 3 prime, which is A3 e to the I, which is here, theta 1, 3 minus pi. As a matter of fact, it is simply, it's the negative of this, right? Minus A3 e to the I theta 1, 3. Because as a matter of fact, if in general, if a vector is AB is this one, sorry, let me draw it like this. This has a length of r. If it is r e to the I theta, then BA would be the opposite of that. It will be minus r e to the I theta, as you can guess. It's a vector in the opposite direction. And, well, you can, these are equivalent, by the way. This equation and the equation I have written in the previous page, which is this one, okay? They are equivalent equations. Only thing is the variables might be a little bit different. You know, I might be using theta 1, 3, or instead of theta 1, 3, I might be using theta 1, 3 prime, but they are the same equation. And their solutions would be the same. Okay. We will come to the solution. I will write you something else. We have enough time for that. Let me try to do that as well as a last thing for today. There is another mechanism which we will consider, and that is the inverted slider crank mechanism. It is the following. This is the simpler version. Sorry about this. This is a terrible drawing. Well, supposedly, this has to go through here and go like this, so that Let's say this is A0, this is B0, and this is A. Okay. Okay. And this distance now, since this slider slides not with respect to the ground, but with respect to link 3, we call it S. The previous one was S14. Now this is S34. Okay. 4 is sliding with respect to 3. There is no A3 here, by the way. I have to erase this because S34 is the link. Theta 1, 3 is yes. So the loop closure equation is a simple one here. Let me draw it here. It's a very simple triangle. A0A is equal to A0B0, which is a fixed link length of A0, A1, let's say, plus B0. Okay. So I can write e to the, sorry, A2 e to the I theta 1, 2 is equal to A0, B0 is a fixed length of A1, A1 plus S34 is the link length, e to the I theta 1. So if you separate the real and imaginary parts, it is A2 cosine theta 1, 2 is equal to 1 plus cosine theta 1, 3. And the imaginary part is okay. So problem is given theta 1, 2 for theta 1, 3 and yes, not 1, 4, 3, 4. We didn't start solving them yet. We just have formulated. This is the easier version of slider crank, inverted slider crank mechanism. I will do a more complicated one the next time. Yes. In theory, it is possible to solve for these unknowns. Okay, let's stop here for today.